Welcome to another GC Basic tutorial for the 16F175 chip family. This is part 11, I2C or I2C operations discovery. So we're going to look at how to discover devices on what's called the I2C or I2C bus. It builds upon what we've seen in the past, but it is a different protocol. It is a different part of the microcontroller, so it's an interesting part. Please like and subscribe these videos. I'm in it for these likes and the subscribes. Thank you very much. Okay, 11. Look, we're nearly over halfway through. So all we're going to do this time is discover some devices that are attached to the microcontroller. Subsequent to that, we'll do a load of, we'll look at the operations of that GLCD display. But that's what we're going to find. We're going to find discovery an I2C device. So I'm assuming that you've installed the software. You've got that software all working, and you can program that 16F175xx. You've got some LEDs, potentiometer, and a switch. You have a USB TTL converter. We're going to be using that, and this time I've actually hooked up a GLCD I2C device, a display. And I wonder if I've got another one. I might dig out another one, and we'll have it in my hand. So what is I2C? It's a bidirectional. So it's bidirectional, data coming and going, and it has an open collector or open drain lines. I mean, that means they're set up correctly, and the lines are pulled up with resistors. So the lines are allowed to float to the positive voltage. You have two lines, the serial data line or SDA and the serial clock line, the SCL. Now, typical voltages are 5 volts. I'm going to be using 5 volts, but 3.3 is also very common. And other voltages are permitted. So always check your voltages when you're doing this. And the hardware I'm going to be using, the hardware in terms of the chip itself, is I'm going to attach it to port C. I'm going to attach the SDA, that's the data line, to 5, and the clock line or SCL to 4. And so it looks like this. I've got two new connections in this little diagram I've been sort of maintaining here. Now, the clock's here and the data line's there, look. What does that look like on my prototype board? Well, the prototype board's got a bit busier. This is a GLC device. It has a number of connections. I wonder if I can zoom in. I might go and get another one, and then I can show it to you. I've been away, and I'm back now. So look, this is a GLCD device. It looks like this, little things. This one is just a sample device. I have got so many I2C devices, I2C devices, but this is just an example. And it has 4 connections, power, a ground, a clock line, and SDA. Those 4. You can just about make out the 4. There you go. Look, here's another one. Looks the same. They all look the same. They are very different. This one has the ground as pin 1, then the VD, then the voltage, then the SDA, and then the clock, then the SDA. So in this one, it's inverted. The voltages are inverted. So this one is VCC and ground. Then this one's ground and VDD. Isn't that great the way they're labelled? This little thing little yellow thing here, tells me not to put more than 3 volts into it. More than 3 volts blows this thing up. This is 5 volt tolerant. This is 5 volt tolerant. When you're doing I2C, you have to be aware of the power. I'll put those down. What have I got? I've got a chip connected here. I've got 4 leads into the back of this into the back of this device here. Let me just rotate it slightly. Oh, I can do it like that. Here we have 5 volts. I've got the ground. Yellow is always my clock line. Blue is always my data line. And they are hooked up into the ports I'm going to be using, C4 and C5. So that's the last time you'll see that, because what our job is to discover what device this is. Now, for those who are playing along at home, you can just about make out a number on the or you can just make it out. It's hard to see. If I zoom in, I already know the address. It says 78. You can just about make it out here. I know the address, but I've got to make sure that the bus is working, and that's the crucial thing with I2C. Because the IC bus, I use it interchangeably. This bus needs to be pulled up high. It needs to be pulled north. So that's what in my brain, that's why I say pull north. So I have my VCC, whatever voltage that is. Remember, on these devices, they say VCC, VDD, interchangeable. 5 volts, whatever voltage it is, you need to pull them up with these resistors here. One resistor here, one resistor here. I've got them pulled up to 4.2K. You can look up that number. There are calculators on the internet. Then you can attach your device on the same data line. So look, the yellow line here comes along and then into the device, and then you can hook more devices into it. As long as they have unique addresses, you can do it many times. The same with the data line. Data line is pulled high, connected to the device, and then it could be connected to more devices. Just erase those. Great. And so in here, I've got, I think it's C.4 and C.5 connected into those two connectors. And our job here is to discover whether that device is actually working in terms of, is the pull-up correct? Is the bus happy? Because if it's not, there's no point of proceeding on to trying to make the GLCD or any I2C device work. You have to get the circuit correct. And it's always good to do discovery first. So what is this sequence, I2C sequence? Well, it's essentially, starts with a green one, it starts, then it sends an address, and that address is what we're going to determine. And then we send some data, and then we stop. And these are signal states that are in the protocol. So there's a start condition, and it transitions the lines in particular ways. Then you send an address, and it sends out the address to say, are you there? And once it responds with an acknowledgement, it can have some data sent to it. And then after all the data has been received, it says stop. Now there is a read sequence, very similar. You would say start, send the address of a read address, and then you do the read operations, and then you would stop. All that is simplified in GC Basic, but these are the important processes that are in place within the protocol itself. So something needs to hold the line, control the lines to generate start signals that then control the SDA and the clock, the data line and the clock line. As they transition backwards and forwards, it tells the bus and the attached component what the state of the line is. So what we're going to do is we're going to have a little display that looks like this. And I'm going to use some of the commands that we have seen in the past to display this type of grey display that you can see on the screen. But what we're looking for is responses. And on a typical bus, you'd have unique addresses. And this is the write address, and this is the read address. You might end up with something down here in a 0 range, and that would typically be memory. You know, you could end up with something down here and here, but devices have all sorts of numbers, and you need to ensure that you can see those and address them, because if you just send data out, you're going to get very frustrated. So discovery is a critical part of the process. So what I do, even with this chip, it's a new chip. I didn't know if the hardware I2C module worked, so I always use software I2C. That helps me set up, make sure all the lines are working, and then I turn to my hardware I2C. For if one works, I know the line. If I use the software and that all works, I know that the hardware should work if my setup is correct for all the hardware components. And the difference between the two is a different command set, obviously, but one is more robust. The hardware is more robust. Let's go out to GC code and get some coding done. Hit the Windows key, GC code, start up, GCStudio. Great, let me zoom in on that for you and take the 16F175xx chip range demonstrations, and it will take us into the IDE. Blank screen. So what are we going to do? We're going to do software, and then we're going to do hardware. So Control B or open up the Explorer. Choose how you like. And now I've given you two 170s as well. Show hardware I2C and show software I2C. And they both send it to the serial terminal. So we want the software to start with, double click it. And I'll take the other one, double click it, go back to my software and shut down there. So what are we going to do in here? Well, all the green stuff is all the commentary for you to read in your leisure. I have got this section here, and I'm specifying my chip. Option explicit means I need to define my variables. And then I initialize, using init the PPS that we've seen before, I initialize the hardware serial, but there's no hardware I2C yet. We'll look at that in the next demo. Now all of this is in the help, but these are why these demonstrations are quite useful, because they're reference code. So I've said here, I want to define I2C as software. And these are the commands I use. I define 4 constants. The mode, which is master, could be a slave. I won't talk about that. Sorry about that. I2C data, I2C clock, they're physical. You tell it which ports it is on. And then generally I would disable the interrupts. So 4 constants, mode, data, clock, disable interrupts. They're all there. Just press the help. Now, these are the serial setup, which we've seen before. And I've described, I'm going to just go into the code itself. So I've defined a byte, a device ID byte, because we're going to send out 255, we're going to test for 255 different I2C devices. We've seen the HCR command set. These are sending strings to the terminal. And this is a header. It's going to produce a top row hexadecimal address on the top. If you remember in the PowerPoint, we can see that. I'll just show you in PowerPoint what that looked like. And that's going to, get rid of my, erase that. What that's going to do is, in here, it's going to draw that line out there. All this, that's all it's doing. Then it's going to format it, put a 0 out, send all the code out, put another format, send all those out, and it's going to walk through. So here we go. Device line was the variable that we defined. It's a byte variable, 0 to 255. Typically, addresses of 8 to 119 are used. Now, they are 7-bit numbers, so I will update that in a moment. They are 8-bit numbers, so that would be, I'll change those to 8-bit numbers. Yeah, I've changed those. Typically, they're 16 to 239, and they could be hexadecimal numbers. We're going to see them in hex for formatting reasons. Okay, we can see that in here, it's going to display our little line for us. And what we're doing, quite clever, okay, it uses the modulo 16 here to determine whether the device ID is 0. If it's 0, it puts out that little thing on the left-hand side. And then we do some commands, look. I2C start. It sends out the start command. The green one we saw in the PowerPoint. It sends out the device ID. This is part of the protocol. Sends out the device ID. Then, if the state is true, then we know it's good. It's there, it's present. Else, we print out two dashes. And then we send out a 0 and a stop. Why do we send a 0 out? Because if you're doing particularly a read operation, you need just to shut down the protocol. And then we say end of search, look here. So we loop through 255 times doing that. We go, oh, did we find it? Put the number on. If we didn't, put 2 dashes out. Right. We're going to compile that pressing function key F6. Not going to program it yet. It has just programmed it. Not programmed it, compiled it. I'm going to press function key F9, or you can take function key F4 and type in terminal, serial terminal, and it will open up the serial terminal. We've seen this before, though. Okay. And I'm going to put that there, and I'm going to move the IDE to there. And where's my terminal gone? Put my terminal there. Now I'm going to press function. I'm now going to press function key F5 to make the hexadecimal file and flash the terminal. Flash the terminal. Flash the microcontroller. It's compiling it. It's verifying it. Boop, job done. Now, if only I'd connected to my TTL. There we go. Let me just push that button. I'll just reprogram it. Be quicker. This is acceptable. Look, we have a device. We have 2 addresses. This is the write address and this is the read address. Trust me, that's all you need to know, that that bus is working. So why don't we look at the hardware version? Now I'm hovering over the taskbar and rotating my mouse and it will take me to the next one. Now, inside of this program, the major difference is we have to set up the PPS. So I've taken the PPS, so function key F4, PPS, and I need to set up the SCL and SDA. I need to be able to attach that capability to specific ports. And so in here, I have all my peripherals. I will zoom in for you. Just let me bring that into focus so you can see it. All the peripherals are listed here. We know SCL, and there's 2 I2C modules. There's the SCL 1 or 2. I'll take number 1, and I'm going to put that on RC4, add it in. SDA 1, it's matching partner, the data line. I put that on 5 and add that in. And we need the serial as well, TX1, and I have that on C6. That is exactly the same code that we've got inside my program. RC6 is hex 13. You can see on the left-hand side there in the editor. RC4 is 1B. All the other parameters look identical. That's where I got it from. You need to turn on the hardware SC, the hardware I2C module. Let's just get rid of that. Then inside of my code, the only difference in here is I've set up the I2C. Again, a couple of, it's actually 3 constants. You need to tell it what baud rate to use. Always do discovery on the slowest, which is 100. There are many different. Look at your specification of your I2C device. Tell it which data port it's on and which clock port it's on. Again, if you get confused, just refer to the demonstrations or to the help. And then, for this type of device, we have to set those points as inputs. I wish I could work out whether they're inputs, but it's down to a chip family, and these particular chip family is an input. Others are outputs. So always look at the demonstrations. It's a real good resource. So I'm saying here, set that port as an input because these are the constants I had defined previously. And then I tell it the mode is a master. I2C mode master. And then the code is extremely similar to sort of formatting. And rather than using I2C star, it's got an H in front of it for hardware. Sends out the device ID as before. It gets an acknowledgement. It sends a 0, either a dash or whatever, and then it stops. It's quite simple. So we knew the software won't work. So if the libraries work, this will work. I press function key F5. Notice this says Software I2C, and now it's changed to, let me just get that a bit larger for us, Hardware I2C, and it's found exactly the same two addresses as it would. And I'm going to be using hardware throughout all these demonstrations, but you can use software, just change the command set. Now, what is important to note is if I go back to the software, I want to go back to my software version here. I don't know why my mouse is not working. I'm going to go back to shut that down. Here's the show software versions. If I reprogram now, I want to show you this, because this is important to understand. It's reprogramming the software that we knew worked, but it's not working now. Look, there's nothing here. It's empty. It got no responses back. That is because the PPS is still set in the registers have not been reset by the programming cycle. So what you should do, if you really want to be perfect, is always turn off the PPS by setting everything to 0. But there is a quicker way. Let me open up PIC16F175xx. Just power cycle the chip. If you power cycle the chip, it will set the PPS to the default of 0, power cycle it, and look at that. They reappear as if by magic. That is a real trick. So if you're going between hardware, PPS, and software or something, always power cycle the chip. Good. So we've done some discovery, we found some devices. That means that next demonstrations we can show you some graphics. That's where we were in my slides. Did all that lot. We did the software, we did the hardware. Next, let's look at some graphics. Enjoy.